Hey, it's Abdul. Welcome to another video in the BIOSTATS CRUSH course. Today, we're going to be going over the standard error of the mean. So this video won't have a solved question just because this topic is very self-explanatory. So let's just dive right into the basic core concept. Now, one unfortunate reality of the world that we live in is that science, at the end of the day, is imperfect. Ideally, if we want to do a study, we should be doing it on the complete population, but that's very unrealistic and honestly practically impossible. So to circumvent that, we do our studies on a smaller sample of that population and then start praying and hoping and double crossing our fingers that this sample is a good representation of the population and that our findings within the sample will correspond with the actual population. So as scientists, as researchers, our goals is that we want our findings in our study to reflect the true effect in the population of interest that we have. So what I'm trying to say is, in a very kind of like roundabout way, is that we want our dataset study mean to equal the population mean, but obviously that's never going to happen. So we want the mean to be as close to each other as possible. We want the distance between the study sample mean and the population to be as small as possible. Now, what the standard error of the mean is, or the SEM for short, is a measure of the distance between the study mean and a population mean. And the mathematical formula for that is the standard deviation divided by the square root of the sample size. So using a bit of mathematical magic, we can tell that if we want our standard error to be as small as possible, we can either decrease the standard deviation or increase the sample size. Now, realistically, when conducting a study or conducting a trial, we can't really play around with the standard deviation because that's a finding that we get after the study is done. The only thing that we can control is the sample size, and that's exactly why scientists love seeing those big RCTs with a lot of people with those big sample sizes. It's because the bigger the sample size a study has, the smaller that standard error, and the more likely we are able to have our effects correspond with the population's true effects. If you're watching this video and you're like, okay, that's great and all, that kind of makes sense, but what's a confidence interval? What's this confidence interval that pops up, and how is it related with this the standard error of the mean? Well, I'll tell you. Scientists have the standard error of the mean, and we have the study mean, and we try to find a way to combine those two together to kind of correspond that to the rest of the population, and we do that via a confidence interval. Now, a confidence interval is just going to be the mean, okay, the mean that we got from our study, the study mean, plus minus the standard error of the mean times by 1.96. This 1.96 being a constant. All this maths jargon aside, the true value of a confidence interval is the following. For any given measure, 95% chance that the population will fall within our confidence interval. If this sounds kind of confusing and you're pulling out your best dunk expression, then that's absolutely fine, because we're going to go through another stupid and goofy example, right, to kind of understand this concept. So let's just imagine for a second a hypothetical version of you, a very based version of you, sitting down at the orb of pondering, and you realize, and you make this kind of like statement, right? A little thought, perhaps. Rugby players are pretty damn smart, all things considered. This is a very valid thought, but obviously you're going to have to prove this with a study. The population of rugby players worldwide is given around 8 million. And obviously it's impossible to do a study on all rugby players, so you take a sample of around 100 people, right? And you hope that this sample will represent your population. Now, you run a study, you give them all IQ tests, and you have a mean IQ of around 106 with a standard deviation of 4. So far, not bad. You calculate the standard error of the mean and you times it up and you add it up to the mean, and now you have a confidence interval, a 95% confidence interval that goes from 105.2 to 106.8. But what does this mean? This means if I grab a random rugby player from the rest of the rugby player population, there is a 95% chance that his IQ will fall between 105.2 and 106.8. This is why confidence intervals are so awesome. They allow you to take your dataset mean and extrapolate that data to the rest of the population. Now, in this same scenario, if I redid the study and did it with a sample size of maybe 1,000 people, then maybe my standard error of the mean would be even smaller, and then the confidence interval will be even more accurate. So again, the confidence interval tells us for any given measure, there is a 95% chance that the population will fall within our confidence intervals. Now, the MBME can be sneaky bastards at the best of times, and sometimes that 95% can be a bit confusing. What I mean by that is a lot of students sometimes get confused between the 95% of a confidence interval and the 95% of the 68, 95, 99.7 rule of standard deviation. To clear that confusion for you, the 95%, the range where 95% of our data set falls under, that's going to be 2 standard deviations above and below the mean. The range where 95% of the population falls under, and the keyword here is population, that's going to be your confidence interval, so just be aware of that. And that wraps up kind of like the basic core concepts of this topic, just having a quick look at the in practice. And just like measures of dispersion, the standard error of the mean is absolutely everywhere you look. Open up any study and there's a good chance you're going to find some degree of confidence interval. This study is done by Dr. Sims and Dr. Sauter, the GOATs, and some of the greatest orthopedic surgeons I had the pleasure of working with. They did this RCT in Saskatchewan where they looked at the effects of superficial versus deep local anesthetic in patients who are having a carpal tunnel release, and you can see when they're presenting their scores, the pain scores in 24 hours, you have a 95% confidence interval. What does that mean? That means if I go to a random patient who received deep local anesthetic for carpal tunnel release, there is a 95% chance that this patient's pain will be between 3.09 and 4.7 in 24 hours post-op. Another example, this is a big study done looking at patients who had trauma and presented to the hospital with hemorrhagic shock, and they received pre-hospital plasma. You could see here that in the abstract, the overall survival benefit was a hazard ratio of 0.65 with a 95% confidence interval of 0.47 to 0.9. This means that if I take a random trauma patient with hemorrhagic shock who received pre-hospital plasma, his survival hazard ratio, there's a 95% chance that his survival hazard ratio will be between 0.47 and 0.9. As a general rule, if an outcome is given as a mean plus standard deviation, this will tell you a lot about the measures of dispersion within the study sample and tells you a lot about the study itself and how valid it is. This is a good example of a descriptive statistic. However, if that same outcome is given as a mean plus confidence interval, the researchers, the authors, they want to tell you how to apply this measure to the rest of the population, and this is an example of inferential statistics. And with that, we are finally done with this topic. Thank you so much for listening. If you found this video useful, please leave a like, comment, and subscribe, and hit the bell icon if you want to get a notification every time I drop a new video on this channel. If you're interested in mentoring, whether it's for step 1 or step 2, use the code CLED. The first 5 people will get 20% off their first mentoring session. And with all that said and done, thank you so much for watching and have a great day.